All right. We got some alliteration in the title, which is always a good start. So this talk's going to be about harnessing your hardware with SIMD. So SIMD is one of the 19 WebAssembly proposals that are is currently in flight. It's one very near and dear to my heart because I've been working tirelessly on it for the past like 9 months, almost a year, something like that. I lose track of time. So much SIMD. So I guess yeah. Me. I'm Thomas. I'm on the WebAssembly tools team here at Google, normally down in Mountain View. And I work on LLVM and a thing called binarian, which makes your WASMs go fast. And generally working behind the scenes on scripting, but my work also makes Rust go faster and anything else that happens to use LLVM to compile the WebAssembly touches stuff I do. So it's a fun job, and making it all happen behind the scenes. So what is SIMD? Probably some of you know, since you're like, oh, that's interesting, I'll come out and hear about it. But maybe some of you don't know. So SIMD stands for single instruction, multiple data. Okay, well, what does that mean? So say I have 2 arrays, normal arrays of integers. And say I wanted to go through and for each index in these 2 input arrays, I wanted to compute the sum of the numbers and store it in an output array. So I would write a for loop, and I would iterate through my input arrays. And on the first iteration of the for loop, I would get that 6, and then I'd get 102, 53, and I just go through one at a time, right? This is what loops are good for. You know, that was a lot of work. I just had to click through like 8 slides just to add those 2 arrays together. So wouldn't it be cool if we could do that a little faster? So notice here, single instruction, multiple data. Well, what do we have here? Multiple data, thank you. And what were we doing to those multiple data? Single instruction. Okay, so this is a perfect use case for SIMD. With SIMD, we're going to come in and we're just going to add 4 things together at once, and then we're done. And then we go and we add the next 4 things together, and then we're done. And I only had to click through 2 slides. Okay, so that's how SIMD is faster than not SIMD. Right? Any questions about that? That's good. They're basically, these I would claim are all isomorphic to one another. So you may have heard of Moore's law. Moore's law says that the number of transistors on the chip, whatever, gets doubled, you know, every so long. Maybe it's 12 months, 18 months, who knows? Anyway, it's wrong now. And so, you know, how do you make things faster if you can't, you know, just double clock speed every year? Well, you just do more of it. That's basically what SIMD is. So all the fancy new chip features, it's just more SIMD. Yes.
That's 7 up there.
Well, that would be difficult, wouldn't it? And we'll actually to that later. Yeah, I'm on top of it. I anticipated that question. So, right, SIMD. It's an idea that's been around for a long time. You see Intel over here, AMD, someone, x86 people introduced SSE back in 1999. And actually, Power beating them to the punch in 1996 with their VMX and AltiVec extensions. So, you know, you may have heard of x86 and ARM. Turns out these things are not locked in stone and never changing. People keep adding stuff to them. And a lot of that stuff is SIMD. So you can see the x86 has had a ton of different SIMD extensions added. And most recently, AVX 512 gets you 512 bits in each one of those SIMD vectors, which is quite large. In this example, we had 4 times 32 bits. So this is a 128-bit vector. So basically, on a real x86 chip, you can get even 4 times faster than this nice example. So I only would have needed half an instruction to add these two arrays together. Pretty nice. I didn't want to like type out longer arrays though. That would have been difficult. So WebAssembly, right? We are a sort of a virtual instruction set architecture. So we're not MIPS, we're not ARM, we're not Power, we're not x86. We're something that is an abstraction over all of those, but also needs to be implemented in terms of each of those, right? So SIMD, our goal is to let you take advantage of your hardware. So one thing we could have done is said, okay, all of these, we're going to implement all of them. All of them. Just every single SIMD instruction anyone has ever made, we're going to put it in WebAssembly. And if you're running on a platform that doesn't have that instruction, we'll just emulate it in terms of other instructions and it'll all just work. That's one thing we could have done. That would have been hundreds and hundreds and hundreds of instructions and a huge pain in the butt. And 10 years from now, we would still be in phase 1, just trying to spec it all out. So we said, no, we're going to take the minimal portable subset from all these things, the smallest chunk of instructions that's actually usable and useful for something. We're going to spec that first. We're going to get it through the process as quick as we can. And while that's going, we can have our crazy dreams about what comes next. So this means, what do we have? All right. So how do we decide what goes into the proposal? Well, as a group, we've decided that different groups of related instructions can come in all together, and they'll be separately validated to see whether they should be included. And for each one of these groups of instructions, that group should bring a performance win on multiple relevant architectures, whatever that means, right? And what does that mean? Whatever the community wants it to mean, right? These are very human processes, not rigorously defined, which allows some nice flexibility. And if in that group of instructions that you're trying to bring into the spec proposal, there is a slow instruction that maybe is extra slow on some architecture, maybe even slower than if you had scalarized it and just done it one lane at a time, then, well, that could be okay, but you better justify it. All the other instructions better be really fast on all the architectures. Side note, I hope Ben's presentation showed you that the whole spec process, how we put this thing together, is like super mundane. It's just a bunch of people who get together every couple of weeks and we just like hash it out. And everybody has different goals and different opinions and different priorities, different ideas. And we all just kind of muddle around and hash it out over time, right? And
I think it's exciting.
it is exciting. When I say mundane, I mean, like the spec does not like come down to us like from on high, like in perfect form and can never be changed, right? No, it's like a human process. We're just putting the thing together, right? So that means every single one of you, if you've got a great idea for what should be in WebAssembly, that idea is just as good as everybody else's ideas. There's no like masters of WebAssembly who just like know better than everyone else. No, it's like a group effort. So you should totally bring your great idea to the CG and participate. And as Ben said, yes, it's fun. Okay, digression over. Anyway, yeah, that's the inclusion criteria for the SIMD proposal, which we decided on as humans. We're like, this seems like a good idea, so this is how we'll do it. This is how we do everything. So what do we get? We get one new value type. You may have heard of I32s and F32s and I64s and F64s. Well, those are the value types in WebAssembly. Those are the things that you can write into memory, read out of memory, pass around in locals, and a bunch of other craziness involving stacks. So we had a new one, V128. It's a 128-bit vector. Pretty simple. Along with that, we get 4-lane interpretations. So you got 128 bits, just a bag of bits. It's what you treat them as, that's important. So you may have noticed that we have an I32 type, which is just a 32-bit integer. We don't say whether it's signed or unsigned. It can actually be either. And it just depends on what instructions you apply to that I32. The instructions bring the interpretation. Is it signed or unsigned? Same with the vectors. So we've got instructions that interpret these 128 bits as 16 I8s, or 8 I16s, or 4 I32s, or 4 F32s. So there's a great bit of flexibility here. Also means we have a lot of instructions. So how many instructions? Well, currently 108 instructions. We can load vectors. We can store vectors. We can create vectors. So like if you give me an I32, say 5, I can splat it, which means I create a vector that has a 5 in every lane. Splat. I can extract things from the vectors. I can replace things in the vectors. I can do lane-wise comparisons. So in WebAssembly, if I do like I32 dot, I don't know, dot EQ equals, that's going to give me either 0 if they're not equal, 1 if they are equal. For vectors, if I do I32x4 dot EQ, and I'm comparing two vectors for equality, it's going to give me back a vector. And that vector is also going to have 4 lanes. And for each lane on the input vectors that were equal, we'll get all 1s in the output vector. Not 1, all 1s. 32 1s. And for anything that's false, we'll get all 0s. That lets us use the output vector as a sort of mask. So then we can do an AND with that vector and some other vector, and that's how you can sort of kind of do different things to different lanes without having to take your vectors all apart. We can add them, we can subtract them, we can multiply them, do a whole bunch of other stuff on them, like min and max. If you ever run into Bill Budge, ask about min and max with vectors. It's quite a story. We can do floating point arithmetic. We can like take their square root and stuff. It's a lot of fun. We can also convert vectors like 32-bit vectors. Sorry, like F32 vectors to I32 vectors. Do that kind of conversion, and we can shuffle them up. Given a vector, I can rearrange all its lanes, make a new vector out of it. Yeah. Question was, when I say lane-wise comparison, I'm referring to the thing from the previous slide. Yes. So when I say lane-wise, I mean like, exactly, yes, like for each of these 16 lanes, 8 lanes, etc. Yeah. So 108 instructions. Most proposals add 6 instructions. And so part of the reason that this proposal is such a beast and has taken so long in the standards process is just its surface area, right? This is a huge number of instructions to implement in engines, to implement in the tools, to write spec text for, to write spec tests for, to implement in the reference interpreter. There's all this work we have to do, right? We have to document them, right? That's a lot of words to write. So it's been a long time coming, but thankfully we just got to stage 2 at the recent June meeting. So progress is being made. Okay, so that's what SIMD is, and that's what kind of SIMD we have right now coming through the pipeline in WebAssembly. What questions are there about any of that? Yes. Aha, what about 64-bit types? You may have caught in Ben's presentation, but you probably didn't, that we removed all these 64x2 operations in the latest meeting. They were in there. If you go look at GitHub, they're actually still there, but technically we have voted to remove them from the spec. Why did we do that? Well, if you go look at the inclusion criteria, there's a lot of stuff about justification here. And so we did not have the benchmarking numbers necessary to justify, according to this criteria, inclusion of the 64x2 operations. That's both F64x2 and I64x2. However, we hope to have that data very soon and add them back in. They're just not technically part of the proposal right now. I wouldn't want to lie to you and said they're in the proposal, because they're not. But that'll be fun because that'll bump this count up to like 150. So, it just gets better and better. Well, any other questions? Yes, thoughts? Yeah. Yeah, that's a great question. So the question is, we have 16 by I8 lane interpretations, but WebAssembly doesn't have an I8 type. So all the instructions that put stuff into a 16 by I8 vector or take stuff out actually just pass in an I32 or receive an I32 with, it's high 24 bits just like chopped off. So yeah, when I do a replace lane to insert an I32 into a 16 by I8 vector, it ignores the high 24 bits. And when I do an extract lane to get that value back out, I can choose whether to interpret it as signed or unsigned. There's different instructions for both of those, so I can get it back either sign extended or 0 extended. So it's totally flexible, but so it comes back as an I32. Yes? Yes, the question is, why limit ourselves to 128-bit vectors? I have to say, SIMD's been in the works since SIMD.js way back in the day, and I was not around then, so I don't know all the history. We have some folks who were around. Actually, do you want to answer that question and give a better answer than I could? Do we have a microphone? Yeah.
Yeah, portability is a big part of it. The Neon target is 128-bit. That's sort of the consensus length among other Ultivec, other platforms. And the idea also is that if we go to longer, it's like that's when we start getting into territory with the long SIMD techniques. I know, are you talking about long SIMD in your talk?
Nope.
Okay. Anyway, it sort of morphs into a different kind of problem when you start looking at longer vectors of generalizing to like dynamic size lengths and that kind of stuff. So there's kind of a different design consideration there.
Okay, so now you're all experts on SIMD, which is awesome, but what can we use it for? So lots of things, as it turns out. As these stock graphics will inform you, you can use them for cryptography, for physics simulation, for image and video and audio processing, and just sort of generic data processing. So literally anywhere where you have a lot of data, you might say multiple data, and you want to do the same thing to all the data, single instruction. So all of these applications, which are pretty cool. Now, not all of us are running around writing world-class cryptography libraries. That's okay, but a lot of us are hoping to use them. So a lot of SIMD will come to you via libraries, and you may be able to ignore the rest of the talk because you'll never use it directly. That's okay, That's a perfectly valid way to use SIMD. Others of you are writing these things, or you're just curious and want to experiment with SIMD. Yes, you do. And so then the rest of the talk is going to tell you how to use the SIMD to do these things, or other things. Yeah, so I mentioned data, right? Justification. So I'll just share some of that data. We did some benchmarks, yeah, so Skia is a 2D graphics library. It runs all of the graphics for Google Chrome and a bunch of other stuff. So it's important that goes fast. And we compiled it with Emscripten to WebAssembly with SIMD enabled and disabled. And then we ran it on a bunch of platforms. And I say we, but actually it was DeepD. Thank you, DeepD. And you can see it got faster, between 2 and 4 times faster. So if this was a perfect world, and this was mostly using 32 by 4 instructions. So in a perfect world, it would have just gotten 4 times faster because you're doing 4 times as much work in a single instruction. And of course, that's not the case at all. So it's very noisy, and the tests are doing a bunch of other stuff, and the code generation isn't perfect, and there's like a whole bunch of issues. But look, that's a real speed up that we observed on real stuff. Yes, question. There are no GPUs here, only CPUs. Yeah. There are no GPUs. Yeah. There are no plans for GPUs that I'm aware of either. Oh, Dan has a plan.
Like so you talk about long SIMD, GPUs are a long SIMD device, right? So that's kind of one of the questions is like, do you generalize this to GPUs?
Yep. Yeah. So in theory, you could have a WASM engine that like takes all this stuff and says like, oh, look at this vector code. I'm gonna combine all the vectors together and make even bigger vectors, and then fork it over to the GPU to run it. In practice, I don't think any WASM engine does that, but you could go write one, and that would be cool. TT.
I just wanted to add that, especially like we don't have those here, but when you have neural network benchmarks or some kind of things that actually use the GPU quite intensively, even for those type of benchmarks, they do find it useful to have SIMD enabled on their CPU workloads, because when you have a smaller kernel and you just want to do a limited amount of work, it's actually more performant to use the CPU workload instead of like the overhead of going to the GPU and back. So we've had those benchmarks are not ready to share, but we do have use cases like that I think are in that, I guess that's kind of the in that space exactly. Yeah.
It's also important to note that here we're comparing WebAssembly with SIMD to WebAssembly without SIMD, and we're not comparing anything to native. So even like compared to like if you did native build with SIMD, like it would just blow this out of the water, or by like a couple X. So yeah, we're not comparing to native yet. Come back in like a few years. We've optimized the heck out of these things. Right, so Skia, cool 2D graphics library, does color management, does it faster than SIMD. Halide is a language for image processing. It's a DSL that's like embedded in C++. They actually have a WebAssembly build, which is pretty neat. Again, we built the WASM stuff with and without SIMD, and it got faster. Less fast because these benchmarks, these kernels are doing other stuff as well. But pretty promising, Intel laptop chip, phone chip, random ARM development chip, like still got faster. So we are getting cross-platform speedups here, which is pretty cool. So Halide has this benchmark, which does something, and this benchmark, which does something. This one's interesting because one of them got slower, but we have a great excuse. Our implementation is not complete yet. So all the things that needs to go fast, we just haven't done yet. But we will do them, and then it'll go fast. We promise. And right, and then there's this benchmark where things go fast again. There's this benchmark, and there's this benchmark. And you can see like it's just going fast for all these different workloads. Don't ask me about the workloads, but they're all different. And they all I'm told, use different sets of our SIMD instructions. So this is like pretty broad coverage of the SIMD proposal. And it goes fast, so that's great. Great, now you know what it is, what you can use it for. Missing bit is, how do you do that? So I'll show you. First of all, are there any questions? No, steam right ahead. So obviously, you have to program in some languages. You have a choice of languages here. You can use C and C++, where we have this WASM SIMD128.h intrinsics header that you can include And then that provides a bunch of functions that, after it goes through all the compilation, will map down each function to a single SIMD instruction. So you get total control over what WebAssembly code comes out the other side. In Rust, you can do a very similar thing with the SIMD crate. And assembly script also has support for SIMD. I think it's just like built-in functions. You don't really need to even do anything special. So for the rest of this talk, I'm going to dive into an example using mscripton in C, using this WASM SIMD128.h intrinsics header, which has been a work in progress for, I don't know, like 6 months or something, and landed 2 hours ago. So this is, thank you. So this is hot off the press. It was a great community effort. The pull request where we were developing this has like 99 comments on it over the past like 2 months. And this is just since we started developing it on GitHub, like we were working on it before then. And it was a great conversation, very productive, lots of different ideas, nobody arguing past each other. So this was a great example of a community effort between a whole bunch of different people, Google, Mozilla, random internet people. It was really great. So thank you to everyone for making that happen. And this is just how we work, right? So you too come in and get in on these great conversations to push WebAssembly forward. So here's a loop. It's in C. This is actually a loop that would implement that first example with the 2 arrays that are getting added together. So we just take, we have a destination array and a source and another source array, and we know the length of the arrays. And so this is a normal scalar loop, no SIMD yet. We're just going to loop over the arrays and add elements from the source array and store it in the destination array. So let's vectorize this. So first step, include that header, WASM underscore SIMD128.h. So it just landed in upstream mscripton like 2 hours ago, as I said, which means it's currently going through our release CI. And sometime tonight, our bots will pop out a brand new tip of tree mscripton release. So if you try this like tomorrow morning, I'll show you in a bit, but you can actually use this as soon as very soon. If you pull from GitHub directly, you can use it now. So okay, next step, we're going to use some of those functions that were defined in that header. So notice, not only do we have functions, we have this new type v128 underscore t. This is a new C type that represents one of these WebAssembly v128s. We can call this load function to load from memory one of the v128s. We do that for both of our source arrays. And then we call WASM underscore r32 by 4 underscore add, which, as you might guess, adds the 2 together. And then finally, we call store to put it back in the destination array. So that's it. We just load them, added them, stored them. It was that simple. And how would you know what functions to call? Well, at some point we'll have documentation, but for now you just go look in the header. It's really straightforward, I promise. Like the instructions just say what they do. Yes, Ben. So what you have to do, since now you're stepping through 4 items at a time, you have to go back, and if there are any leftover items, go through them sort of one at a time and do the normal scalar code. So really what we've done is just blown up our code size. We have the same loop from before, and now we've added also a SIMD version of the loop. There's other tricks you could play, like you could just like back up the pointer a bit and then like add them again. Like because the loads and stores don't need to be aligned, so you don't really need like a second loop. You could pull some other hack, but whatever, you're gonna have to add some code to fix up the ends. So it is a little bit of extra stuff to think about. So how do I build it? Well, for those of you who have used Emscripten, this should look awfully familiar, using the EMSDK to install the toolchain. Tot upstream is tip of tree upstream. So when I say hot off the press, I mean it. That's how you install the latest and greatest that we've put together. And then you can't just build it because it doesn't know what SIMD is. You have to tell it, hey, use SIMD. So that's what this -m SIMD 128 does. It just tells the compiler, hey, enable this SIMD feature. So that's pretty cool. It'd be nice if it was simpler. So instead of rewriting your code, you could just do this, add that O2, and the compiler will automatically do that transformation for you. Right? So the exact same code we had here, we didn't need to write any of that. We could have just stuck with this, and then when we do -O or -3, -O2 or -O3, the compiler automatically does that for us. So that's super cool. And all of those benchmarks I showed you before, where things got faster, just auto-vectorized. Nobody wrote a single line of handwritten intrinsics or built-ins or anything in line assembly. Nobody did any of that. It was all the compiler auto-magically doing its stuff. So that's pretty powerful. Literally all you need to do, since you're probably already passing -O2, is add this -m SIMD 128, and boom, your code might get faster, maybe, if it's a good if it's a good sort of candidate to be vectorized. Most of your code probably isn't, and it won't get faster. That's okay. Yes. Yeah, it does. Yeah, so it'll totally bloat your code and everything to make it go fast. Yeah, it totally handles that. Oh, sorry. The question was, does the auto vectorizer handle the case where you have 7 elements? Yes, it does. Okay, so we built it. Now we need to run it. So unfortunately, this isn't quite as straightforward. It requires, for now, launching Chrome from the command line and manually passing in these JS flags to tell the engine, hey, use SIMD. Pretty soon, or right now, if you're using Chrome beta, you can also just go to chrome://flags, and there will be a nice UI toggle to just turn on SIMD. Then you load up your WASMs just like normal, and boom, SIMDized. You can also run on the command line if you get, so, I would show Node here, and Node does take this -- experimental WASM SIMD flag, but this is all such a fast-moving work in progress that even the latest Node is still got some slightly out-of-date V8, so there's going to be a bunch more SIMD bugs than there are in the current V8. So I recommend for now, until things stabilize a bit, running your workloads, your SIMD workloads using D8, which is like the V8 debugging shell. You can get it from JSView or wherever you get your JavaScript runtimes these days. Also, I hear that Chakra and WAVM have complete SIMD implementations, including those 64x2 operations. I've not played with them myself. That's another option. Right, okay. I'm sure there are questions about using this stuff, so what are they? Okay.
So maybe a two-part question. What, if any, relationship is there to SIMD with threads?
Mm-hmm.
And the second part is, what about environments that may not have multiple cores? So like a outside the browser in an environment that is single core, single threaded.
Yeah. So SIMD does not require threads. It doesn't. When you use SIMD, you're not spawning another thread to do the extra operations. It's literally just a single core on your CPU just doing a whole bunch of things at once, but still just one core. So this is a different kind of parallelism from multi-threading, where in multi-threading, you can have a bunch of threads, so maybe different cores on your CPU. They'll all be doing different instructions. That's the difference. This is single instruction only, whereas multi-threading can be different instructions going on independently. So the good news is that means if you turn on both threads and SIMD, you get the speed up from both, and they like stack. So that's a pretty good deal. Yes. Yes. So yeah, if you did -m SIMD 128 and then also passed -pthread, you would get a vectorized multi-threaded application out. However, there's no like automatically, magically, multi-thread your application. You actually have to write a multi-threaded application to take advantage of that. There's no auto vectorizer for multi-threading. Not that people aren't working on that. It's just like not a thing right now. That's great. Any other questions? Yeah.
So with EMCC, you could add a -02 and it auto-magically vectorizes for you and uses SIMD, and that's great.
Yep.
And thanks, by the way, for doing all of this work.
To be clear, I had nothing to do with the auto vectorizer, but you're welcome.
Could WebAssembly runtime, since it takes the WebAssembly and runs it in some kind of native platform anyway, do that same kind of work, preventing this sort of work?
That's a good question. So in theory, it totally could. And for a lot of these offline applications where you get the WebAssembly module and then you compile it once and you take as much time as you need to really optimize it, and then you store the native code, and then you run that like a billion times based on network requests or something. I'm thinking like the edge computing case. You totally could. And I feel like I've heard of a product where they take the WebAssembly, feed it back through LLVM, run all the optimizations on it, and get a binary out. I'm not sure. Maybe one of you works on something like that. But yeah, if you're doing it ahead of time compilation, that's totally a legit thing that the runtime could do. Now on the web, we really care about compiling fast. There's like a caching story for binaries, but like a lot of times you're just recompiling them and you're trying to get the interactive performance. So compilation needs to be fast. So we're not taking the time to do that kind of optimization. Maybe we will in the future. I don't know. But that's not the kind of thing web VMs are doing right now. Any other questions? Okay. All right, so what's next for SIMD, right? We're just at phase 2, so there's a long road ahead of us. Well, we got to put those 64x2 operations back in. Some people really want them. They're important. There's also a bunch of other instructions that people want to get into the MVP proposal, which is really cool. And if there's an instruction you really want to see in the proposal, go make sure it's there. And if it's not, let us know, and maybe we can get it in. So some of these new instructions just combine two existing instructions. So like load and splat, for instance. Well, we have a load instruction and we have a splat instruction, but we don't have a load and splat instruction. And so if we have load and we have splat, why would we need a load and splat? Well, it's because the web VMs aren't doing anything fancy. They're not pattern matching. They're not detecting that you've got a load and then a splat. They don't have time for that. So they can get better code if they see a single load and splat instruction rather than two different instructions that they have to pattern match on. So that kind of thing is totally fair game to add to the proposal. And then new capabilities like fuse, multiply, and add. Kind of similar. We have a multiply, we have an add. Turns out FMA is a little different from that. So that's also something that we're working on getting in. And what do we need to move on to stage 3? Well, we need spec tests, which are being worked on right now. However, as I said, there are a lot of instructions. So if you want to help write some spec tests and move this proposal along, that would be awesome. You are totally welcome to contribute to that. It's all out in the open on GitHub. We also need spec text. So someone needs to take what we have and make it more formal. And then eventually, we don't need it for stage 3, but we definitely need it for stage 4. And it would be nice to have as soon as possible a reference interpreter implementation, the spec formalization, and more implementations. Right? We have a few. We need more. And we need more complete implementations. So if you have a WebAssembly engine, go implement SIMD. It only takes 6 months, I promise. And come tell us about it. And maybe we can send some users your way, get you some nice bug reports. Yes, that was my slide where I was taking notes on things to make slides on. Yep. So finally, this is totally a community effort. So I just want to call out in particular Deepti, who's been totally awesome getting this going, pushing things through, organizing stuff, doing all those benchmarks. And then a whole host of other people. Thanks a lot. It's been quite a community effort. And it's exciting to see how much velocity we've built up into this proposal. So I'm excited for the near future. So now that you're all WebAssembly SIMD experts, go tinker with it. Go try it out. And let me know if you have questions. Like now, or when you try it out, and then you have issues, still let me know. I want to know about the issues. Thanks. That's all I got. What do you have for me?
For example, loop to be vectorized is not the same as the vectorized code that you showed.
Oh, bummer. I wrote it really fast. Where's the bug?
Pointer aliasing.
Pointer aliasing. So is the issue that we are loading v128t's from what should be an int, and therefore it's undefined behavior? No.
No, the
Oh,
issue
if
is that dest and source A can be overlapping. No. Okay.
Oh, yeah, destined
Yeah.
source. Yeah, I didn't even think of that. Good point.
That's true. And actually tying into someone was asking about, could you re-vectorize from WASM in the engine? And the engine has this problem too.
Yeah.
Where, and it's actually even worse in the engine, because here you actually have some C rules about at least type A listing can apply depending on how you interpret it. Or maybe the programmer could add restrict keywords and help you out.
Yep.
WASM has no restrict keywords.
That's correct. Yeah. So, yep. There's always more information earlier in the compilation pipeline because it can only throw away information. It can't create it. So, yeah, that's very true. I guess we should all go use Rust.
It's not a question, and I know you hate when people say not a question, but actually, if you go to Compiler Explorer, you can actually take that code and run it with M128, and I bet you it might work.
This particular code won't, because Compiler Explorer doesn't know about my nice header.
Oh, not this code, but if you try and auto-vectorize that code, it probably will generate something that makes... Deepti says it works.
Yeah, it works. Because of the restrict thing, it might not work on this exact code. But in general, yes, if you go to the Godbolt Compiler Explorer and select the WebAssembly from the little drop down, and then put the -m SIMD128 in the little flags box, then yes, you will be able to see SIMD come out the other side. Yeah. Okay, yeah. So actually, I did compile this code, and it totally created a whole bunch of WebAssembly at the other side. So that must be what it was doing. I didn't really read it that closely because I was trying to write slides, but yeah, I think it does actually check for overlap and do all this crazy stuff in addition to fixing up the ends. So yeah, that loop got quite large due to the auto vectorizer, but hey, it's fast, so it's good. All right, well, come talk to me if you've got any questions or thoughts. Thanks, everyone.
Cool.